who is coming from the University of Arkansas, and he will take us into a little discussion on the dynamics of polar vortex crystal formation. Almost time to go.
Thank you, Professor Martin, for the introduction. Is this one? Okay. Thanks. So good afternoon, everyone. I'm Suyash Rijal, a PhD student. So my name is Suyash Rijal. I'm a PhD student in the Laurent Bellis group at the University of Arkansas. I would like to thank my advisor, Laurent Bellis, Professor Sergey Prokorenko, and Professor Yusha Nahas for the opportunity to work in such exciting projects and for their support and guidance. I'd also like to thank the Department of Defense and Arkansas Research Alliance for funding this project, and also Arkansas High Performance Computing Center, where we performed all our simulations. The topic of my talk is dynamics of polar vortex crystal formation in ultra-thin films. So first I'm going to give you a brief history of the polar vortex crystal. So polar vortex crystals were first found theoretically in PZT ultra-thin films back in 2004, about 2 decades ago. And then relatively recently, they were found in PTO-STO superlattice. So these structures, they form spontaneously under the right balance of elastic and electrostatic conditions, and they can be tuned by several parameters like strain, thickness, electric field, screening. So with all the right ingredients, ultra-thin films of ferroelectric materials like PZT and STO, PTO, superlattice, we have these vortices spontaneously forming. Okay. So at low temperature, we find this vortex structure, and if cooled slowly, so upon annealing, we find such structure, and like abruptly cooling down from high temperature to low temperature, the system could also go to a labyrinth-like state called the labyrinth state, where there are no like stripes seen. Rather, stripes are seen on both the in-plane direction as opposed to one direction as seen in the top figure. And both these structures show like remarkable periodicity. The one at the top, as you can see, it's periodic along the x direction. The one at the bottom, it shows like there are domains, but you see it's periodic along both the in-plane directions, and they're like the domain size is kind of fixed. So and upon heating both these structures at high temperature, like above the Curie temperature, they melt down and form. They melt down and form, like get to a liquid-like state where the system, it does not know like which direction to prefer. But if you see these snapshots in time, they're like happening one after other, and it does not know. It's a melted state. And this was taken from this paper, Nature paper. Okay. So polar vortex crystals, they are extensively researched for their tunability and their prospective technological application. They show interesting properties like collective vortex zone excitation. That was quite recent. Their coupling with light and electrons. As I said, they show remarkable periodicity, and the vortex tube stacking, and well, abrupt cooling leads to labyrinth state, which is like a glass-like state. However, it shows like remarkable ordering. So that all that leads us to think that okay, at high temperature it melts, at low temperature it forms like order. Is there something related to it? But we don't understand the origin of it quite yet. There is a consensus that I mean, we all know that there is a depolarizing field that does not allow polarization, all polarization along one direction, so the system form vortices. But that's not the complete story. At least we thought that that was the motivation behind the study. And the question we asked is, are these condensed wave patterns like how spin spirals are in magnetic systems? So yeah, so with the motivation, we move forward. Okay. So the method of our investigation is we use effective Hamiltonian molecular dynamic simulation on lead zirconate titanate alloy with 40% zirconium and 60% titanium. We use a 32 by 32 by 5 supercell. So this is ultra thin, 5 unit cell along the Z direction is about 2 nanometers. We have -2% compressive strain. So what compressive strain does is epitaxial strain. So it makes sure that the preferred polarization direction is out of plane direction, and we have 80% screening of surface charge. So that with that recipe at low temperature, we find the stripe state as such if we cool down slowly. Okay, so this structure up top at top left over here with the blue and green tubes is what in literature is called polar vortices or polar stripes, but they are basically the same thing, just different ways of thinking about it. For example, this, for example, see my mouse. Okay, this if you look at this figure over here, you see the vortices. This is the xz plane of the figure up top over here. You see like clockwise and anti-clockwise vortices. If you take a xy cross section of this structure, you see stripes of up and down dipoles forming periodically. So in one way, it can be thought of as polar stripes. In the other way, it can be thought of polar vortices. But for the rest of my talks, I'm not going to say any of it, but I'm rather going to call it vortex tube crystal, because these are you can also think of it as like these vortices stacked along the y direction in this figure, making tubes of clockwise and anti-clockwise vortices stacked right next to each other. So I'm going to call them vortex tube crystal. And now if you look at the XY cross section over here, and also now follow along this box, here is the zoom figure along that line. You see that the dipoles are like rotated in a sine-like fashion, so they are harmonically modulated. And if we take a structure factor of this dipolar configuration, we see two bright spot non-zero spots along the x direction, and the magnitude of the wave vector, it corresponds to exactly 8 unit cells, which is also the periodicity of the wave pattern that we see in the real space picture. So here, if you take any of the dipole and go 8 unit cells along the x direction, you find the same copy. Okay. So with that in mind, we extract the spectral energy density from molecular dynamics, from the statistics we obtain from molecular dynamics. So spectral energy density basically is the average kinetic energy per unit cell, and it's a wave vector and frequency is resolved. With that, we obtain phonon dispersion relation for the dynamics of this vortex tube crystal, VTC. I'm going to abbreviate it from now. So not only we obtain the spectral energy density, but we separate the contribution coming from the vibration of different dipole components along different direction. So if you look at the left panel, that corresponds to the vibration contribution coming from the vibration of X component of dipoles along the x-axis, along the x-axis, yeah. And if you look at the right panel, those are coming from the vibration of Z component of dipoles also along the x-axis. Okay. So if we look at the lowest branch and the minimum of the lowest branch marked by the yellow circles in both the images, we see that they also correspond to the periodicity of 8 unit cells, and interestingly, they are coming from the modulation of X and Z component vibration of the dipoles. So they should correspond to, if you look at the XZ face in the bottom panel, they should correspond to, you see, like the modulation of the dipoles in the XZ plane is such that the Z component and the X component of the dipoles are getting modulated along the X direction. So these modes, the ones marked by the yellow circles, represent the modulation of the X and Z component of the dipoles. So they must be somehow contributing to the formation of these vortices. Okay. Next, we extract the eigenvector associated with the mode that I just talked about in the yellow circle. So here is how you understand the picture. The gray cones are the static part of the static part. So those are the dipoles, and the red and blue cones are the dynamic part. So at any time t, if you look at any time t, all the dipoles, they are like collectively modulate, increasing along the direction of the red cones, the one closest to them. So what the red cones represent is the change, the coherent modulation in all the gray cones at one instant, say t equals to t prime, and after a certain time, tau over 2, they coherently modulate along the opposite direction, which are represented by the blue cones, and they happen in a cyclical fashion. So so they are like collectively growing, rotating, and then growing again in the opposite direction. So these eigen vectors represent, and also they come from the X and Z X and Z component of the dipole modulation. So they are associated with the formation. They should be associated with the formation of the vortices, the vortex tube crystal. Okay, with that, we are even more excited that okay, we found the mode that are responsible for the vortex tubes. So next, we look at the this vortex tube crystal mode and how it behaves with change in temperature. So if we heat up the system, as you can see in the frequency of the mode versus temperature figure, the frequency is softening up to certain temperature, which is the transition temperature of the system. And then again, if you're coming from the other side, like if you're cooling, you also see similar behavior, that the mode is softening up to the critical temperature, and it also like nicely follows this square root of Tc minus T behavior, which is consistent with the mean field approximation of soft mode theory. So with that, we can like now confidently say that okay, this is the mode responsible for the formation of vortex tube crystal in PZT films or in ferroelectric ultra-thin films. Okay. So now, if we look at the structure at 400 Kelvin, which is above the transition temperature, at a first glance, it looks like, okay, this is a disordered structure. But if we look at the structure factor of this panel, XY plane, XY cut, we see that it has like a ring-shaped structure factor. And now, as I told you before, such ring-shaped structure factor, as I told you before, like at temperature above the transition temperature, the system melts and it's in a liquid-like state. So this structure factor reinforces that idea, and this means that okay, the system it does not know, it prefers like a certain modulation or of a certain magnitude, but it does not know which direction to prefer yet, or which direction to prefer in that temperature. Okay. I have only 5 minutes, my watch is telling me. Okay. Okay. I'll go quickly from here. So now if you look at the spectral energy density at um, plots at 400 Kelvin, we see that all the plots are identical with each other, like coming from the X component modulation, Z component modulation, Y component modulation, and also along the X or Y direction. So this shows us that the system has like an isotropic nature at that temperature, which is also consistent with it being like a liquid-like state. And also, if you look at the mode, the soft mode, you see like close to it, it has like a linear behavior, which is reminiscent of a gapless Goldstone mode, which happens when like a continuous symmetry is broken. In our case, translational symmetry is broken, and also discrete rotational symmetry of like 90 degrees is broken, and so we see like a low-hanging mode at this temperature. So with all this knowledge we have so far, we see at the application of this idea, and what we notice is that the vortex tubes along the X and Y direction is system chooses arbitrarily at the transition temperature. So we ask, okay, can we switch it from being parallel to Y direction to being parallel to X direction by some external probe? So to do that, we choose the frequency that I point over here at the gamma point, and we choose and also electric field in the direction perpendicular to the periodicity. So in this case, over here, we're applying electric field along the Y direction to switch the vortex tube from being parallel to the Y direction to being parallel to the X direction. So it does not happen right away. It goes through some transient states, but yes, we are able to switch it from this state right here to this state. So what happens here is, as we apply the electric field after a certain time, so we're applying electric field along this direction, these vortex tubes, they shrink they shrink and they move in the opposite direction, and simultaneously there is like a meandering wave, dipolar wave, forming along the direction of the applied electric field. And after a certain time, when the electric field comes to zero, we see that this structure, the tube radius increases again, and they align in the central plane. Certain time later, they do the opposite thing, right opposite of what's happening here. And if we switch the field off, we successfully rotate the structure by 90 degrees. Okay. 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 And yeah, so these parameters characterize the switching. So QXB is a parameter, order parameter that that we pick out, which corresponds to the periodicity of the vortex tube crystal along the x direction. So if you look in time, this is dying out, and simultaneously the parameter corresponding to the same periodicity along the y direction is growing. So this shows that we successfully switch the vortex tube, and also this can be explained by a biquadratic coupling between this parameter and the polarization. And with that, I would like to summarize my talk. So vortex tube mist crystal form from condensation of the vortex tube crystal mode. It's an optical phonon mode, and they are in the condensed wave pattern. So that's kind of like a paradigm shift, because they are not just ensemble of polar domains, but rather condensed waves, and they belong to a harmonically modulated state family, like spin spirals or charge density waves or magnetic fields in liquid crystals. And entire vortex tube crystal can be rotated by 90 degrees by an application of external AC electric field, and this kind of like opens possibility for phonon engineering in this system. Thank you for your time and attention.
Okay, time for the questions.
Thank you for the talk. I have a question about your physical structure pattern. We're looking at the frequency as a function of the reservoir, but you're looking at different components. That's why I'm using it. And I believe your investigation was a divine isotropic. And I was wondering how is that possible when